Jim's in Glasgow and Francesco.
Oh,
And
sorry.
Francesco's in Italy, in Milano Blanco. Okay. So before I get into actually describing the embedding, I'm going to describe Thompson's group T and T bar because they're super useful. And almost the talk is an excuse to talk about that. Okay, so T, which I think maybe was mentioned in an earlier talk, was one of the two first discovered finitely presented simple groups discovered by Richard Thompson in the 1960s. Okay, so there's got to be a better way of doing this. Yeah, there we are. T is a group of homeomorphisms of the circle. So when I write S1, I mean the unit interval with 0 and 1 identified. So it's that circle. My circle has circumference 1, it doesn't have circumference 2 pi. Okay, so all those homeomorphisms of the circle that are piecewise linear and their slopes are powers of 2. So all the slopes are powers of 2. And there should only be finitely many breakpoints. And all the breakpoints should lie in Z adjoin a half, which means the intersect the circle. So that means all the breakpoints have to be rational with denominator a power of 2. And we want to setwise stabilize the dyadic rationals intersect the circle. This exists to avoid irrational rotations. It's common even for experts to forget this condition, but it's necessary. I include myself as someone who's forgotten this condition in a talk. But you don't want irrational rotations. Okay. Definition of T bar, I'm going to make unnecessarily complicated. First, we're going to define F to be the map from homeo, the real line, and this little plus. When I include this plus, I mean orientation preserving. Okay, no flipping things. Okay, so F is going to be the map from homeo plus of R, orientation preserving homeomorphisms of the reals, to orientation preserving homeomorphisms of the circle. But we don't want all homeomorphisms of the reals. We just want the ones that commute with x goes to x plus 1. So the periodic ones, periodic with period 1. And what we want to do is, whenever gamma is an orientation preserving homeomorphism of the real with period 1, and it maps some number x to some number y, then x mod 1 should get mapped to y mod 1. So it's exactly the homeomorphism from periodic maps on the reals to homeo of the circle that you would expect. Okay, and then T bar, I'm going to give two definitions. One of them is just the lift of T to the line. So it's the periodic homeomorphisms of the reals that look like elements of T, as in everything's, well, this is the other definition. It's the ones that get mapped down to T. So all the slopes should be powers of 2, should be finitely many breakpoints, all lying in the dyadic rationals, and setwise stabilizing the dyadic rationals. So T is the one of the circle, and that's finally presented in simple, which is a nice fact. And T bar is the one of the line, which is finally presented, but it's not simple, but it is perfect. It's not simple because it has the translations by 1 as a center. So that's definitely a normal subgroup. Okay, no questions? Okay, I'll probably give an example of some elements in a moment. Okay, T bar has this, has this very nice presentation, just 5 relations. And I think I'm going to go to here. So where am I now? Oh yeah, and then T bar has a presentation with only 4 relations until just these 2 generators alpha and beta, and they're not like that. And I'm going to try and draw an element. So that's not the drawing tool. That's definitely the drawing tool. Right. So this is our circle. Alpha to the 4 looks like this. So these are all dyadic points. Let's say that's 0. This can be a quarter. 3/4. Then alpha just maps each interval to the next interval. Okay. And beta is similar, except it only has 3 intervals. So alpha is just rotation by 90 degrees, whereas beta, we still map each interval to the next interval. When you're going from this interval to that interval, it's a terrible beta, you have to double the length. That's fine, still a slope of power of 2. Okay, so why does the presentation if you have questions or I go too fast, then do interrupt me. Okay. So why does T bar have a presentation that looks so similar to the presentation for T? It's because T bar is a central extension of T, which means that there's a homomorphism from T bar to T, where the normal subgroup is the center. So that means that each relation in T gets turned into a relation in T bar, except when the product in T equals the identity, the product in T bar equals some element of the center. So that's basically why you lose a relation. Okay. I'm going far too quickly. I always do that. Okay. So the Higman embedding theorem. Higman embedding theorem is one of the coolest theorems. It says that if you're interested in, I suppose I should say what solvable word problem means. That would be sensible. Okay. So Higman embedding theorem says that if you have a finitely generated group that has solvable word problem, if and only if it embeds into some finitely presented simple group. I'm going to assume people know what simple and finitely presented means. Solvable word problem means that the set of words which represent the identity over our finite generating set is recursive. Not just recursively enumerable, but recursive. We can check for membership and check for non-membership. Okay. This is a beautiful theorem with it's amazing. It's amazing that he even thought this was a sensible thing to try and prove. Then it's even more amazing that he managed. And the proof is quite complicated and involves describing normal subgroups in. Oh, someone said something in chat. No, it isn't. When what I said probably included the word simple, that's because I'm an idiot. In this amazing instance, the slides are correct. But thank you, Alan. The Higman embedding theorem embeds things in finitely presented groups. There's something called the Boone-Higman conjecture, which says that, oh, no. You were right, my slides are wrong, but in a different way. That's irritating. Okay, I can fix this down here, though. Okay, so this, I suppose what I've actually, so this should probably say recursively enumerable. Sorry. Okay, so that is you can check if something's the identity. You can't necessarily check it's not the identity. Thanks, Alan. Hi, Alan. I've not seen you in a really long time. Okay, so this theorem makes sense in that if something's finitely presented, then you can check things are the identity. In that you just the things that are the identity are the things that are products of your relations or other conjugates of your relations, finite products of conjugates of your relations. And you can just check if something's a finite product of a conjugate of a relation because there's countably many of them and you can just list them. Okay. So that means you can check things are the identity, but if something's not the identity, you can't check that. Okay. So that's the Higman embedding theorem. The Boone-Higman conjecture, which is a super interesting thing, asks, is the analogous theorem true in the way that Higman embedding describes recursively enumerable word problems, groups, as ones that embed in finitely presented groups? The Boone-Higman conjecture asks, can we describe actual solvable word problem groups, one where we can solve, as in show things are the identity and show things aren't the identity? Are they exactly the groups which embed in finitely presented simple groups? And for an only marginally more complicated argument, it's clear that subgroups of finitely presented simple groups do have solvable word problem. And that's a nice puzzle if you want to try and work out why that is. But that's unknown. We don't know if all solvable word problem groups embed into finitely presented simple groups. That's a super interesting question. Okay, so Higman embedding describes finitely presented subgroups of finitely presented groups as the ones with recursively enumerable word problem. Boone-Higman conjecture would describe subgroups of finitely presented simple groups as the ones with actually solvable word problem, solvable both ways. Okay. Okay, but the Higman embedding theorem is actually stronger than this corrected version because in one of the directions he proves something stronger. He proves that if something has a recursively enumerable word problem, then it still embeds in something finitely presented. So you can have subgroups of finitely presented groups that don't have solvable word problem, like basically you can just play around doing something like just choosing a group which has maybe a direct power of all the prime cyclic groups of prime order, and then just take a subgroup that has only certain primes, and then the certain primes being some horrible non-recursive set, and you'll be able to learn something about that set if the group had solved a word problem. So when you try and put infinitely generated groups into finitely presented groups, you can put a lot of information in exactly what set you're using. So the other direction doesn't go. But you can embed any countable group into any solvable word, so any recursively enumerable group into a finitely presented group. Okay, so in particular, you can embed a Q, the additive group of rational numbers, into a finitely presented group. And then Higman's embedding theorem does that. But Higman's embedding theorem is quite complicated, and it is constructive, so you can follow it through. People have done this and find an actual presentation for a group that Q embeds in, but it'll be a horrible embedding that won't tell you anything at all about Q or anything. And the presentation will be disgusting. It'll have lots and lots of complicated relations. Okay, but Higman was interested in this question and was actually also put in the Copenhagen notebook. Go back to my slides. Okay, so people were interested in this question, including Higman. Then unrelatedly, some other people, which is Belk, Bob, and Matucci, looked at T and they embedded Q over Z in T, unaware of this embedding of Q question. And they were doing other things as well in this paper. Okay, but it turns out if you just take this embedding of Q over Z into T, and then just take the lift of that copy of Q over Z to T bar, then you just get a copy of Q in T bar. So there was this situation where there was a set of people who knew the answer and a set of people who knew the question, and they just happened to not intersect. And Francesco, Jim, and I were the first people in that intersection. So we were mainly just really lucky. And the moral of the story is you should read a list of problems like the Copenhagen notebook because it just tells you what people are interested in. Okay. Okay, so now I should, actually, before I do the embedding, I'm going to go, yeah, okay. Okay, so the actual embedding. Okay, so we need an actual presentation for Q to begin with to make things easier. So there's no questions? Not yet. Okay, so we want Q1 to just be 1, and then Qi is going to be 1 over I factorial. Okay, so this is a very nice presentation for Q because each generator is just a root of a previous generator. So as long as you find a new element which is a root of the previous one, then that kind of means everything works. It's much easier to do it this way than to do like 1 over n, which would be another maybe more obvious generating set. Okay. Okay, so each I, we're going to find a qi in T bar and a partition of the reals as value intervals. And this partition is going to be stabilized by the earlier qi. Okay. And qi itself, the so the partition is going to be stabilized by qj with j less than I. I've just used I and j the other way around in the slides. Sorry. And then this partition determines qi, as in the pi partition determines qi because qi just maps each component to the next component. And we can do that because I suppose I've glossed over what I mean by dyadic intervals. Dyadic intervals means an interval of a length of power of 2, beginning and ending at a dyadic rational. And we can definitely map each one of those to the next one because we just have to stretch or contract by power of 2. If it was like of length 3/4, you can't naturally map that to something of length 1/2, but as long as we're dyadic intervals, we're fine. Okay, so P1 is just the partition which partitions everything up into integer intervals between k and k plus 1. And the way you get the next one is you just pick the interval that begins at 0 and you cut it into I pieces. I should say pi plus 1, shouldn't it? Okay, I plus 1. Someone said something? No. I should say I plus 1. Okay, and then each time you just, okay, so we've cut this interval into I pieces, and that sort of forces our decision for the remaining intervals because we want this partition to be stabilized by all the earlier qi. So we just cut them up in the same way. Where the same way, I can describe what that means. If we have some interval here and we cut it up like this, and we have some other interval, we should do the same thing. So, okay. So that way each thing is carried across in the right way. Okay, so that's the end of what I've written slides for, but there is some other stuff I should say. Okay, so that's just remarkably easy. And I mean, Higman is also famous for the Higman-Thompson groups, which are, so Thompson didn't actually, he wrote unpublished notes, including these finally presented simple groups, T and V, and also this other group that people care about a lot, F, but he never actually published them, which didn't really happen until Higman came along and published them with a generalization. So Higman was just so close to an embedding of T because I don't know if he was aware of T bar or not. So an embedding of Q in a finally presented group because he knew definitely of T because he wrote on it. But the next question Higman would have asked if you'd said, look, we can embed Q in a finally presented group, is he'd have thought about the Boone-Higman conjecture and said, okay, can you embed Q in a finitely presented simple group? So because Q has solved a word problem, not just recursively enumerable word problem. So it should be possible to embed it in a finitely presented simple group. And so that Jim and Francesco and I have also done that. And the trick involves the automorphism group of F. And the automorphism group of, I should have said what F is. F is just the stabilizer of a point in T. So F is the unit interval version of T. So piecewise linear maps from the unit interval to itself, all slopes powers of 2, all breakpoints being dyadic rationals, so on and so forth. So if you imagine taking T bar and modifying it such that you only need to be periodic near the ends. So if you take the commutator with translation by 1, you want the support of that commutator to be a long way away from 0, or at least some distance from 0. Right. No, I've got that exactly wrong around. You want the support of that to be close to 0. So away from 0, it should commute and look like T bar, but close to 0, you're allowed to do anything you like, as long as you still have slopes powers of 2 and breakpoints dyadic rationals. And this makes a very nice group. And the reason it's the automorphism group of F, this is a result of Matt Quinn, the proof is that there's a very nice theorem of Rubin that people who care about groups of homeomorphisms care about a lot, that says that if you have one group that acts on 2 topological spaces in a sufficiently nice way, where sufficiently nice means very transitive, and your topological spaces need to be sufficiently nice, which turns out to be very weak conditions, then the spaces are actually the same, and the actions are conjugate. This is a really cool theorem of Rubin. And that means if you have 2 actions of F on the interval, where one of them is the normal action of F, and one of them is the automorphized version of the action of F, then that automorphism somehow has to be a conjugation. So that means that all the automorphisms of F really have to be homeomorphisms of the interval, just conjugating F. And the way I described auto F just then, I described on the real line, but it really lives on the interval with, am I making sense or not at this point? You're politely not nodding. Okay, I should probably wrap it up at this point. But it's basically possible to put T bar on the circle by squishing it down onto an interval and then throwing that in with a copy of T and generating a new group, which turns out to be finally presented in simple and is nice. And this trick of, okay, I will go into that. Okay, sorry for getting a bit incoherent at the end. Thank you very much for tolerating me. Any questions?
Okay, let's thank James first. Are there any questions for James? Okay. I guess I'll ask, so this is about embeddings of Q in, I suppose, simple groups. Is there any sort of, do you have any sort of general method that will work for other recursively enumerable groups? Or, I mean, it won't work in general, but.
So, I mean, the Higman embedding theorem is a general method to embed recursively enumerable groups into finally presented groups. And it's fairly unwieldy, but it does the job. Really quite unwieldy. But it would be super interesting. So the Higman embedding theorem, the kind of technology it uses is H&N extensions and amalgamated free products and understanding subgroups of free groups well and this kind of thing. It would be really cool if there was another, to reprove the Higman embedding theorem, but using the kind of technology that I like and like my area likes. There's only really been developed much more recently than Higman's time of building weird groups of homeomorphisms, and there's lots of tricks to build them up. So hope maybe it might. So one thing we would like to do is reprove the Higman embedding theorem using groups of homeomorphisms rather than amalgamated free products and H&N extensions. And the real reason we'd like to do that is we'd like to do finitely presented simple groups into. So we can do. Does your group contain box-like solitaire groups? No, but it is. Is that true? No, but it's possible to do that, I think. All right. Yeah, it should be possible to do bomb stack solitaire groups using these kinds of methods.
I was meaning, can you
Because
do it without bomb-stack solitaire subgroup? Like your construction probably has some bomb-stack solitaire subgroups. Can you make sure it doesn't have any in it?
I see. So the version that's in here, so T bar, I don't believe that contains any bomb stack solitaire groups.
Does it contain anything of the form A semi-direct Z where A is locally cyclic?
So could you repeat that?
So A semi-direct Z where A is locally cyclic.
When locally cyclic means what?
Subgroup of Q.
Oh, I see. I don't think so.
Okay, cool.
Because the sorry.
Okay, cool. I said.
Okay, I see. Okay. Which is kind of surprising, I guess. That is the kind of natural thing you would want to try if you were to do it by brute force, as opposed to stumbling on the finitely presented group and the embedding and then noticing it.
Yeah. I'll send you some emails about that then. That's okay.
Oh yeah, certainly. I'm very happy to talk about anything.
Wait.
Are there any other questions for James? Okay, just like me asking the same sort of stupid question, like just to make sure that I understood earlier. So I don't think I've actually ever read the proof of Hickman's embedding theorem. Is it constructive or is it existential proof?
I think it's constructive.
Oh, okay.
It uses the clean star characterization of recursive linear enumerable sets, and it somehow builds that inside subgroups of free groups, maybe it's normal subgroups of free groups, I can't remember, and then it does something called the Higman-Rote trick at the end that somehow turns that into what you want. I would probably advise you to go to the end first and read the Higman-Rote trick, and then read the rest of the paper, I think. I think it probably makes a bit more sense doing it that way around. It's amazing that he thought to prove it, and it's even more amazing that he proved it. It's a really impressive theorem. Okay, thank you very much.
Thank you. Let's thank James one more time.